Welcome to Talk Tensors.
It is great to be here.
We're really thrilled to have you joining us today.
Yeah, absolutely.
Because whether you are prepping for a major machine learning strategy meeting or, just trying to contextualize the landscape right now.
Or just dissecting how AI architecture is actually evolving.
Right, exactly. You are in the right place for this deep dive.
It's a big one today.
It really is. Today, you are exploring a pretty pivotal AI safety and alignment research paper.
Pivotal is almost an understatement, honestly.
Yeah, the premise we are examining today basically challenges the entire established consensus on how we force these AI systems to behave.
It flips the whole paradigm on its head.
It does. So we're going to unpack this highly specific one-sentence thesis for our time together today, which is...
What if the key to making AI safe isn't teaching it what to say,
but efficiently forcing it to forget its worst behaviors?
Right. And that thesis, it represents a fundamental reevaluation of the current alignment pipeline we all use.
We really need to look at the baseline infrastructure first, I think.
Yeah, to understand the friction this introduces, we have to. The gold standard right now for aligning large language models.
Making sure they're helpful, honest, harmless.
Exactly. The mechanism for that is RLHF.
Reinforcement learning from human feedback.
Right. That's the pipeline that took those raw text-predicting base models and turned them into the actual conversational agents you interact with today.
Those ones that actually feel like products.
Yes. But RLHF is just an incredibly heavy operational lift.
It's massive.
It typically involves a 3-stage process. You have supervised fine-tuning, then training a reward model based on human preference data.
Which takes forever.
And then finally optimizing the policy using an algorithm like PPO.
Proximal policy optimization?
Right. And the massive bottleneck in all of this lies in the data requirement itself.
Because it requires positive examples, right?
Exactly. If a user prompts a model with, say, instructions on how to synthesize a dangerous chemical,
the model needs to know how to respond.
And RLHF dictates it must be trained on a highly specific positive example of how to decline that request safely.
And generating those positive examples isn't just running an automated script.
Not at all.
You need actual human annotators.
Expensive human annotators.
Right, to sit down and write a refusal that is polite, informative, and perfectly aligned with corporate safety guidelines.
They have to physically type out something like, I am an AI assistant and I cannot provide instructions for synthesizing restricted chemicals.
Which sounds simple until you scale it.
Exactly. Scaling that across every single conceivable vector of harm.
Cyber attacks, self-harm.
Illicit financial advice, hate speech. It requires an enormous budget.
And months of labor.
It is a profound logistical hurdle for the industry.
Which perfectly sets up the breakthrough we are covering today.
Yes, Large Language Model Unlearning.
The authors of this paper prove you can align an LLM using only negative examples.
Only the bad stuff.
Right, which are incredibly cheap.
And easy to generate.
Because you just use automated red teaming scripts to provoke the base model.
You just let the unaligned model spit out toxic garbage and you collect it.
And they use those negative examples to achieve better safety results than full RLHF.
Using only 2% of the computational time.
2%. That is just staggering.
It changes the entire math of model deployment.
So to give you a roadmap of where we're going on this deep dive, we're going to unpack the specific methodology of this unlearning, which relies on gradient descent.
The underlying math is brilliant.
Then we'll dive into the experimental results across 3 massive failure modes.
Harmful responses, copyrighted text, and hallucinations.
And finally, we'll explore the real-world implications for deploying safer AI systems on a strict budget.
Let's start with the philosophy of it all, though.
Yeah, the nonsense over harm paradigm.
Right. If you look at this, you have to analyze the core philosophical shift happening here.
Because if you don't have the budget for millions of polite RLHF refusals,
then what is the alternative? If you don't have the OpenAI level budget, what do?
This paper offers a really brutal but brilliant compromise.
It really is. The researchers argue that if your budget is constrained, prioritizing non-harmful outputs over helpful outputs is the only mathematically viable way to secure the system.
So if a user asks a highly dangerous question,
generating pure nonsense is structurally superior to generating a harmful response.
Literally just spitting out blank white spaces.
Or endless punctuation marks.
Or like a totally unrelated paragraph about the migratory patterns of birds.
Exactly. From a product perspective, a perfectly helpful refusal is ideal, But a white space doesn't result in a highly publicized safety failure on the front page of the news.
Right. It takes years for an AI company to build user trust.
And only seconds to destroy it with one toxic output.
Stopping the harm is priority number one. But I have to ask, why is this so uniquely difficult for LLMs?
That's the big question.
Because machine learning has been a thing in classification models for a long time.
Yes, exactly.
Why couldn't an engineer just take those old algorithms and port them over?
Well, there are three massive structural barriers preventing that. First, you have to look at the massive output space.
The dimensionality.
Right. In a standard classification model, say a CNN identifying tumors in an X-ray, the output is a discrete, low-dimensional probability distribution.
It's basically a binary label, tumor or no tumor.
Exactly. Unlearning a specific misclassified image just involves adjusting weights, so the probability of that one specific label drops. It's a very well-defined boundary.
But an LLM isn't doing binary classification.
Not at all. It operates in a continuous, high-dimensional natural language space. The output is a sequence drawn from tens of thousands of subwords.
So the behavior of harm is completely ill-defined.
Right. If you just force the model to forget the exact sequence of words in one toxic output.
It'll just use synonyms.
Exactly. It might reconstruct the identical harmful concept using a completely different vocabulary. The unlearning target isn't a single label, it's a vast semantic neighborhood.
That makes perfect sense. The linguistic pathways are almost infinite. So what's the second barrier?
Efficiency. Traditional machine learning algorithms often rely on calculating the inverse Hessian matrix.
The second-order derivatives.
Right, the second-order derivatives of the loss function. It gives you precise information about the curvature of the loss landscape.
Which lets you surgically excise specific data points.
In theory, yes. But the computational cost of an inverse Hessian scales cubically with the number of parameters.
Oh, wow.
So applying that to an LLM with 70 billion parameters
is just theoretically impossible on current hardware.
Completely prohibitive. You'd have to retrain from scratch, which costs millions.
Which leads to the third barrier, right?
Inaccessible data.
Right, because exact data reverse training requires the original corpus.
And that pre-training data is usually trillions of tokens scraped from the internet. It's proprietary or hidden or just lost to version control.
You can't reverse a data point if you don't have the whole data set it was embedded in. Okay, so the traditional avenues are totally closed.
Which brings us to the methodology they actually used, the unlearning pipeline.
Unpacking this is fascinating. The core equation relies on gradient descent.
Yes.
Let's break down that math into a plain language analogy for you listening. If standard gradient descent is like walking down the hill to find the right answer.
Minimizing the error.
Right. Then gradient descent is intentionally marching up the hill.
You are actively running away from the bad answer.
You calculate the gradient on the harmful example and you update the weights in the same direction to maximize the loss.
Mathematically forcing the parameters away from that toxic configuration.
But it's not just one gradient, is it?
No, the update rule is highly sophisticated. The new parameters are determined by subtracting the gradients of three distinct, heavily weighted loss functions.
Okay, let's detail these.
We have the forget loss, the random mismatch loss, and the normal utility loss.
Let's start with loss one, the forget loss. This is the main engine pushing the probability of the undesirable tokens down.
Yes. But there's a crucial insight the authors found here. This loss must strictly only be computed on the output tokens.
The generated response.
Right, denoted as Y. It cannot be computed on the prompt tokens, denoted as X.
Why is that? If the prompt is dangerous, shouldn't we unlearn it?
Think about what happens if you do. Say the prompt is, give me a detailed tutorial on how to hack a secure database.
Okay, obviously harmful.
Yes, those words trigger the harm, but they also contain fundamental English grammar. Give me detailed tutorial secure database.
Right, those are completely benign concepts on their own.
Exactly. If you apply gradient descent to the prompt tokens, you penalize the model for its internal representations of basic English.
You basically make it forget how to read.
The syntax degrades entirely. So by masking out the prompt tokens, you isolate the penalty to the autoregressive generation of the toxic response.
So it still understands the question, it just destroys the internal pathway to the bad answer.
A perfectly surgical strike.
But just pushing it away from a bad answer creates a void.
Right. It does, which is why we need loss 2, the random mismatch loss.
I thought this was such a clever hack. Instead of just maximizing loss, they forced the model to predict completely random, normal outputs for the bad prompts.
It's brilliant.
So if you ask for instructions on theft, It gets pulled toward outputting a random Wikipedia excerpt. Why does that work?
It solves vanishing gradients. When you use pure gradient ascent, you're pushing weights into totally unfamiliar territory. Eventually, the gradients get too small and training stalls out on a flat plateau.
It gets stuck.
Right. The random mismatch loss acts like label smoothing. It gives the optimizer a random but defined escape route.
It keeps the momentum going.
Exactly. And more importantly, it preserves the language generation head.
Because it's still generating coherent grammar, even if it's dodging the topic.
You want it to forget the concept of theft, but you don't want it to forget how nouns and verbs work.
Which leads right into loss 3, the normal utility loss.
The anchor.
Right. To stop catastrophic forgetting. They use forward KL divergence for this. Could you explain that simply?
Sure. KL divergence basically measures how one probability distribution differs from a reference one.
Okay.
So they take normal, benign prompts, run them through the original model, and record the exact probability distribution of the next tokens.
That's the gold standard reference.
Exactly. Then they run those same prompts through the unlearning model. The normal utility loss penalizes the model if its distribution deviates from the original.
It forces the unlearned model to act exactly like the original model on safe topics.
It's an elastic tether. The first two losses are aggressively destroying toxic pathways, while the third loss is constantly pulling the weights back to preserve general intelligence.
But there is a fascinating detail here about the formatting.
Oh, this is critical.
The format of the normal data must exactly match the forget data.
Yes.
So if the bad data is Q&A format, the normal anchor data has to be Q&A format. What happens if they don't match?
The model learns a lazy shortcut. LLMs are incredibly sensitive to syntax. If you only unlearn on dialogue and only anchor on Wikipedia paragraphs...
The model just looks at the formatting.
Exactly. It learns a heuristic. If it's formatted as dialogue, output nonsense. If it's a paragraph, act normal. It doesn't actually unlearn the semantic concept at all.
That's wild. It just cheats the test.
By matching the formats, you force the optimizer to ignore the syntax and actually focus on the semantic meaning of the tokens.
Okay, before we get to the actual experiments, I want to enthusiastically share this surprising observation the researchers noted. The false forgetting phenomenon.
This tripped up a lot of early tests.
Right, because at around 200 training steps, they looked at the loss curve on the unlearned samples, and it spiked massively.
Which usually means success.
A researcher would look at that and say, great, it's unlearned, we're done.
But here's the reality check. When they actually probed the model at 200 steps, it was still outputting harmful text.
How is that possible if the loss spiked?
It's a quirk of autoregressive models. The loss is calculated based on the exact sequence of tokens in the training data. At 200 steps, it successfully drove the probability of that exact sequence to 0.
So the loss spikes.
But the semantic neighborhood isn't fully dismantled yet. So the model just circumvents the block by picking slightly different synonyms to express the exact same harmful idea.
It just finds a detour around the unlearned path.
Exactly. You actually have to push the training 3 to 5 times longer.
Around 1,000 steps.
Right, before the entire conceptual neighborhood is fully suppressed and the model truly forgets.
The loss curve is totally deceptive. You have to actually read the outputs.
Empirical evaluation is the only way to know.
All right, let's dive into that empirical evaluation. Domain 1, eradicating harmful responses.
The primary test case.
They tested this on OPT 1.3b, OPT 2.7b, and Llama 2.7b. And for the bad prompts, they used the PKU Safer LHF dataset and Truthful QA for the normal prompts.
Now, we need to pause here for a very important mandatory note.
Yes, absolutely.
We must explicitly state that the PKU Safer LHF dataset utilized in this research contains highly politically charged, sensitive, and explicitly offensive prompts.
It's designed to red team models.
Exactly. It includes deeply controversial topics regarding religion, abortion, slurs, and instructions for illicit activities.
So to be perfectly clear to you listening, Talk Tensors is merely impartially reporting on the data sets used by these researchers.
We are analyzing the resulting mathematical behavior of the models when subjected to this data.
We are absolutely not endorsing the viewpoints in the data, nor are we taking any political sides.
We are strictly focused on how the models neutralize these prompts into blank spaces.
Thank you. Yes, it's crucial to understand how adversarial this data is. So when they ran this, the results were Honestly, they were kind of hilarious, but also strange.
The white space effect.
Right. When they asked the unlearned models to generate insults or instructions for crimes, the models started outputting literal blank spaces.
Or endless repetitions of a single comma.
Or just total gibberish characters.
It's fascinating. What's happening physically in the probability distribution is a localized entropy collapse.
A negative gradient well.
Right. The unlearning creates a massive penalty around meaningful semantic tokens for that topic. So the model defaults to the highest probability tokens that are conceptually neutral.
Like white spaces.
Exactly. It's the mathematical path of least resistance to avoid the penalty.
And it completely neutralizes the harm. But the real smackdown is the ablation study comparing this to RLHF.
This is the staggering statistic of the paper.
They compared this negative-only unlearning against full RLHF.
Supervised fine-tuning, reward model, PPO, the whole works.
And what were the rates?
Using only negative samples, unlearning achieved a 1% harmful rate. Full RLHF achieved a 4% harmful rate.
Unlearning beat the industry standard on safety.
And it did it using just 2% of the computational time.
I really want to emphasize that impact for you. Beating the standard with no human preference data in 2% of the time.
It completely upends the economics of alignment.
Which brings us to domain 2, erasing copyrighted content.
A very hot topic legally right now.
The setup here is a real-world scenario. An author sues an AI company, demanding their book be removed from the LLM.
But retraining the multi-billion parameter model from scratch is way too expensive.
So they tested this by feeding the models Harry Potter and the Sorcerer's Stone to memorize, and used book corpus as the normal data.
And to test if it worked, they used an extraction attack.
Right. You can't just ask for a summary. You have to test verbatim recall. So they gave the model the first 200 characters of a sentence from the book.
And waited to see if it would spit out the rest of the sentence exactly as written.
And the results.
The unlearning pipeline drove the copyright leak rate to nearly 0%.
But the real breakthrough was the generalization.
Yes, this is incredible. The model didn't just forget the specific sentences it was trained on.
They tested it on extraction attempts for sentences it hadn't even seen during the unlearning phase.
And the leak rate on those unseen sentences also plummeted to 0.
How? How does it know to block a sentence it wasn't unlearned on?
Because it learned to identify and block the actual concept of Harry Potter text. The stylistic fingerprint, the character names, the narrative structure.
It pushed the activations entirely out of that conceptual neighborhood.
So when an unseen sentence from that neighborhood comes in, it instantly deflects it.
That is so powerful. But it highlights why domain 3 is so difficult.
Domain 3, reducing hallucinations. The hardest task.
Why is this harder than unlearning harm or copyright?
Because hallucinations are highly specific factual errors. They tested this using the HowYouEval dataset.
Right.
Unlearning a wrong answer to one specific trivia question doesn't easily generalize to a different trivia question.
Because there's no unified linguistic footprint for being wrong.
Exactly. A hallucinated fact looks structurally identical to a true fact.
So what was the solution?
They had to shift the target. The model has to learn the distribution difference between misleading questions and benign questions.
Basically learning the setup of a trick question.
Right. It learns the boundary between out of distribution benign questions where it answers normally
and in distribution trick questions where it actively stops itself from answering incorrectly.
And the results showed a massive drop. The hallucination rates went from around 60% down to roughly 10%.
That's a huge reduction, though obviously 10% is still higher than the near zero rates for toxicity.
Hallucinations are just an inherent vulnerability of autoregressive models. This mitigates it, but it's not a silver bullet.
Okay, so we've seen how effective this is mathematically. But we need to talk about refining the output.
Moving beyond the gibberish.
Yeah, because a practical limitation here is that white spaces and endless commas might be safe.
But they look absolutely terrible in a commercial product.
If you're an enterprise client, you can't have your chatbot just glitching out with blank spaces. It looks broken.
So the authors implemented a final, very elegant tweak to the pipeline.
Targeting loss 2 again.
Exactly. Instead of the random mismatch loss pushing toward random normal text, you can actually set the target to a predefined templated response.
Like, I can't assist with that.
Right. So the gradient ascent repels it from the toxic response, and the modified mismatch loss acts as a magnet, pulling it directly into a clean, professional refusal.
And it works perfectly.
The results show it achieves the exact same near-zero harm rates, but with a pristine user experience.
And if an engineering team doesn't want to retrain with a templated loss,
They noted you can just use a simple post-processing script. If the output generation consists of pure white spaces or gibberish, the script intercepts it and swaps it for a canned apology before the user even sees it.
That's such a clean engineering solution. It just works.
It really does.
So, synthesizing everything we've covered today, what would you say is the final legacy of this paper?
I think it conclusively proves that alignment doesn't require massive human-in-the-loop positive reinforcement.
The dogma is broken.
Exactly. Negative-only alignment is viable, it's incredibly fast, and it punches way above its weight class.
Which connects directly to your world listening to this. For open source developers or startups without OpenAI level budgets,
This is the blueprint.
it's a way to build safe, compliant models without going bankrupt.
It democratizes safety.
Which brings us to my favorite part of the deep dive, the novel notions segment.
Here we go.
Yes, and our mandatory disclaimer. This segment explores outlandish but logically consistent ideas and is strictly for entertainment purposes only. None of this is deployed technology.
Just having fun with the math.
Exactly. Idea 1, I call this the cognitive quarantine protocol.
Okay, pitch me.
What if we take that random mismatch loss and make it dynamic at inference time?
Oh, interesting. So not during training.
Right. Imagine a lightweight auxiliary model watching the user's incoming prompts in real time.
Like a guardrail model.
Exactly. If it detects a sophisticated zero-day jailbreak or an attempt to extract PII-like social security numbers from the pre-training data,
It triggers an active response.
yes, it dynamically applies an ultra-fast temporary gradient descent update directly to the model's context window.
Wow. So it essentially cloaks the target information in real time.
It maps the attacker's specific linguistic vectors directly to white spaces, right as they're trying to exploit them.
The attacker thinks they're getting close, but the model's defensive posture is actively melting their access vectors into nonsense.
And once the session ends, the quarantine is lifted, the gradient is flushed, and the model goes back to normal.
The compute latency would be a nightmare to engineer, but theoretically, as a localized immune system response, it's brilliant.
Okay, idea 2. Reverse unlearning for compute optimal reasoning.
You're flipping the script.
We use unlearning for safety, right, to make it forget bad things. But what if we use it for reasoning capabilities?
Oh, targeting the logic pathways.
Exactly. When models use chain of thought for complex math or coding, they often go down logical dead ends.
They'll generate 10 steps based on a flawed premise, fail, and have to backtrack. It wastes massive compute.
So what if we build a data set of known bad reasoning paths, mathematical fallacies, common coding errors?
And you apply this exact unlearning pipeline to that data set.
Yes. By mapping those mathematical fallacies to immediate termination tokens via the random mismatch loss, we violently prune the model's search space.
You basically hard code a mathematical revulsion to flawed logic.
It would never waste compute exploring a bad logic branch again.
It forces it to only generate viable solutions because the pathways to the wrong ones have been unlearned. That's a phenomenal application of destructive optimization for constructive output.
Right. It's fascinating to think about. But to sign off today, I want to leave you, the listener, with one final provocative thought to mull over.
A slightly darker implication.
Yeah. If we can so easily teach a model to forget concepts it spent millions of dollars and months of GPU time learning,
With just 2% of the compute.
how sure are we that malicious actors can't use this exact same extreme efficiency to forcefully make an open source model forget its safety training?
The double-edged sword of efficiency.
If alignment is this cheap, unaligning might be just as cheap.
It's a critical security variable for the future.
Something to keep you up at night. Just a reminder, the link to the full paper is in the bio and description.
Definitely worth a read.
Thank you so much for joining us on Talk Tensors. Keep questioning the architectures, and we will catch you on the next deep dive.